So questions that we kind of know the answers to. Here's something I'm interested in doing. Here's a function. I would like to be able to identify where this happens and where this happens. Right? If I have a function that maps something that I'm interested in, like profit or revenue or cost, I'm going to be interested in maximums. Or here's an average cost function. I'm going to be interested in minimums. So I would like an algebraic way in order for, or a calculus-y way, for me to be able to identify when those things happen, instead of just kind of trying to graph them and look at it and guess. With average cost in particular, we have looked at a method that we might use. But in a purely kind of like geometrical sense, what do you know about these times? The concavity doesn't change at these times, right? But the slope is 0. Right? All of them have these flat lines, right? So maximums and minimums occur when slope is 0. Is that an absolute truth? Could you have a maximum or minimum where the slope was not 0? What's the slope here? It does not exist. Right. What's happening here is that the slope from the left is one thing. The slope looks like -1. And the slope from the right is another thing. It looks like 1. So here kind of at the meeting point, right, where the two come together, there's not a fixed slope. These kind of quick changes in direction mean that the derivative doesn't exist. This is something that we talked about on the first test, differentiability. Right? So maximums and minimums occur when the slope is 0 or does not exist. It feels more complete now. Does this go backwards? If the slope is 0, is it a maximum or minimum? Yeah, a flat line could happen, or yeah, an S-curve type of thing might happen, right? Where the slope is 0 here in the middle, but it's not a maximum or minimum. So it won't work backwards, but these ideas are key ideas about trying to identify where those maximums and minimums occur. And it's worth pointing out that there might be different kinds of maxes and mins. There are maximums and minimums like these, where this is a hill, this value is bigger than all of the values around it. But it's not the biggest value that ever was or will be. As opposed to this maximum, which is the biggest value that the function ever will be. We call these types of maximums absolute or global. If it is absolutely the biggest, if it is the biggest in a global perspective, anywhere, then, right, it's an absolute or global maximum. If you're just a maximum that's bigger than the people that you're around, then you're called a local or relative maximum. I should have maybe written those in the other order. Right? You are a maximum relative to the points around you, or you are a maximum in your locality. You're the tallest kid in the class, not the tallest kid ever. Right? You are the maximum relative to the things around you. So we have relative maximums. We also don't say maximums. We say maxima. That's the plural for maximum. Right. Even though down here I have written maximums, right? Really, this is maxima and minima, because these words are Latin and not English, and this is the way that these particular nouns are declined in Latin. They end in um, so they're declined with an a if they're plural nominative. This isn't a Latin class, though, thank God. Okay, same thing for minimums. A minimum could be local, or a minimum could be absolute. A way that we might talk about maximums and minimums collectively is extrema. They're extreme values. So an extrema, a singular extrema, is an extremum. So a single minima, a minimum is also an extremum. But if I were to talk about all mins and all maxes, I would be talking about extrema. And the key characteristic of extrema is that extrema occur when the slope is 0 or the slope does not exist. That's when they happen.
So that's absolutes?
No. Absolutes or locals. Locals also have that property. So not just absolutes. Huh?
Of extremas?
Yeah, of any extreme. So local extrema and absolute extrema, they all share this property that the slope is 0 or the slope does not exist. And again, the slope being 0 is not enough to guarantee us that we do have an extremum. But if you have an extremum, then the slope is 0 or it doesn't exist. Okay? Not all pets are dogs, but all dogs are pets. That kind of thing. Okay? Well, not all rectangles are squares, but all squares are rectangles.
There you go.
Okay? That kind of thing. All right. So this, in a nutshell, is all of 4.2. And we just did that in 15 minutes. This is what there is to 4.2, except that it gets couched in a little bit of algebra. So let's talk about that algebra.
So this won't be on the next exam?
This will not be on the second exam. Let's consider the function x squared minus 2x. Let's say that we're interested in identifying where that function has local extrema. What might I do? Yeah. Yeah. I know that if it's a local extrema, then its derivative is either 0 or doesn't exist. I'm going to call those times critical points. These are my usual suspects, right? Oh, who did this crime? Round up the usual suspects. That's not to say that one of these will be an extrema, but if it's an extrema, it's one of these guys. So I'm going to kind of narrow the field of possible extremums from everywhere to just a few values. So let's do that. F prime of x is what? 2x minus 2. So I'm going to take 2x minus 2, I'm going to set it equal to 0, and I get that x is 1. Does 2x minus 2 ever not exist? Is there any number out there that you can't double and subtract 2 from? No, there's none. What would make a function not exist? What are the things that are forbidden for us? Division by 0 is the big one. So generally does not exist means divided by 0. Just kind of a heads up. Okay, so 1 is a critical point. Okay. How might I figure out whether 1 is a maximum or a minimum or neither? I know the derivative is 0 at 1. If it were a maximum, what would it look like? If I had a maximum, it would be 0 at 1. And what would it look like just to the left of there? Yeah, I'm coming down, right? So the slope, what are the slopes over here? The slope is 0 at 1. What would the slopes to the left of 1 look like? Also 0? Positive? Negative? They should be, yeah, they should be positive, right? Yeah. So it's 0 at 1. It should be positive over here. What about just to the right? Yeah, over here we should have negative slopes. So maximums are going to increase, have a maximum, and then decrease. So increase, decrease. This is what the derivative tells us about a function, right? The derivative is telling us whether a function is getting bigger or getting smaller, or is staying the same. And so if I could find that just to the left of 1, I had positive slopes, and just to the right of 1, I had negative slopes, that would tell me that it was a max. What do minimums look like? So it's decreasing and then increasing. So negative and then plus. So decrease, 0, increase. So this type of pattern would tell me that it's a minimum. And then neither, they're going to match. Right? If it's not a maximum or a minimum, it's going to increase, and then it's not going to turn around. It's just going to keep increasing. There's not going to be a change in direction. Way off there we go. No change in direction. So if it's neither a maximum nor a minimum, then there just won't be a change in direction. Okay, so here's a number line. F prime of x is 2x minus 2. Here's 1, it's a critical value. What about over here to the left of 1? Are the derivatives positives, negatives, 0, a mix of them? Anybody have a favorite number left of 1? 0 is also my favorite number left of 1. Right? What is the derivative at 0? It is negative 2, right? So at one of these times, the function is decreasing. Is it going to be decreasing for all of those times? So is it possible that the derivative is negative some and then positive some? If you were to move from negative to positive, what would have to happen? you'd have to cross 0, right? Are there any times over here where the derivative is 0? What are the times where the derivative is 0? At 1, right? That's what we found out before. There is one time when the derivative is 0. That means that all of these times over here, well, the derivative is either always positive or always negative. All of the candy in this jar is the same flavor. I just got to figure out what that flavor is. So I'm going to do the same thing I do anytime I'm curious about the flavor of candy. I'm going to reach in, I'm going to grab a piece, and I'm going to take a bite. So I'm going to reach in, I'm going to take 0 out, and the derivative is -2. Do I care that it's 2? What do I care about this value? I care that it's negative. This is telling me that it's decreasing over here. What about over here? Right? Also, all of the candy over here should be the same flavor. So let's find out what flavor it is. Anybody have a favorite number bigger than 1? 2 is pretty good. F prime of 2 is what? 2. Do I care that it's 2? What do I care about? It's positive. Right. That's telling me that all of the time over here, that function is increasing. So what about 1? Is there going to be a minimum, a maximum? Neither. It's a minimum, right? The function is decreasing, it hits a bottom, and then it increases. Right at 1. So f of x has a minimum at x equals 1. Here are other questions that we can answer along the way now. When is f of x decreasing? Yeah, all of the times less than 1. So -∞ to 1. When is f of x increasing? All of these times when the slope is positive. So 1 to infinity. So not only do I know that there's a minimum at 1, but I can identify all the times when the function is getting bigger and all of the times when the function is getting smaller. Pretty cool, huh? This is called the first derivative test for minimums and maximums. You find out what are your critical points, those are your suspects, and then they're going to break up your number line. Here we only had 1 value breaking up our number line, but theoretically we might have 3 or 4 values breaking up our number line. And each of those values is going to kind of break it up into different candy jars. And you just have to go to each interval, find out whether it's getting bigger or getting smaller, and then that'll tell you whether you have local extrema at any time. Seems all right? Not too brain busty, right? We had talked about minimums and maximums being associated with 0 derivatives before. We're just adding a little bit of algebra to figuring this out. We had talked about positive slopes being corresponding to increasing functions before. We've talked about decreasing being corresponding to negative slopes. So really, we've just kind of fleshed this idea out just a touch more. Got some more time. So I'll let you all decide what we talk about next. So we know how local extrema are found. Do we want to see what, so the first derivative has a lot to tell us about the shape of a graph, right? It gets smaller, then it gets bigger, right? I know that this function, x squared minus 2x, looks roughly like this. It gets smaller, it hits a minimum, it gets bigger. Do we want to continue talking about shapes of graphs? Or would you like to see, say, implicit differentiation in application? We talked about implicit differentiation earlier today. Would you like to see why that might ever be useful in real life? Or would you rather talk about derivatives and shapes of graphs? How about hands for implicit differentiation? Sorry, it's so lonely. All right, hands for shapes of graphs? All right, okay. All right, very close. It was a near thing. Right? Option C could be.
I was just kidding, but there is an option C.
More limits? No more limits. I see a lot of head shaking. All right. Let's talk more about the shape of graphs then.